Hi, everybody, and welcome to a module on using the Carnot cycle, using what you're covering in your thermodynamics class. Once you get out and you're a practicing engineer in industry or government or wherever you end up working, I'm going to try to give you 4 examples of some great ideas associated with either producing net power or charging up, improving heat pump or refrigeration capabilities that are great ideas. And you're covering this. You will have the ability to do these analyses once you've covered the basics of Carnot cycles. So let's get going. So I call this Carnot cycle analysis applications. What do these 4 images have in common? So take a second to look at them and see if you in your mind can identify all 4 of these images of real world systems and equipment. Well, of course, you've identified all 4 of these, I hope. And what they have in common is that they are all systems operating in a cycle. So, for example, a power plant, its objective is to make net power and sell it to consumers. The refrigerator, system operating in a cycle, what it's doing is we're taking net power from the grid. We've plugged our refrigerator into the wall, so it's running a compressor, the electric power running compressor, and we're removing heat from your cool substances in your refrigerator and rejecting that heat to the surroundings in the kitchen. Air conditioner, same type of idea. We're removing heat. We're trying to remove or reject heat from inside this home space where the person's hand is, and we're rejecting that heat to the outside. And what it costs us is plugging the air conditioner into the wall. A heat pump, a similar idea, except for a heat pump, what we're doing is we're pulling heat from the outside. We're adding it to the electric power energy or power we're buying, okay? And we're moving that heat transfer into our house. We're trying to heat our house with a heat pump. And so I want to give 4 examples of using the Carnot cycle analysis to your benefit as a practicing engineer that you will be soon. Okay, exploiting the power of Carnot cycle analysis. If you have not done so yet, I want to encourage you to watch my Carnot Cycle 101 video that gives the technical background behind these 2 sketches. So I hope you're comfortable with these 2 sketches and recognizing quickly how are they similar and how are they different. Let's see, similar. Well, they're both black boxes and they're systems operating in a cycle. Over here on the left, this would be a power cycle. And how do we know that? That's because W.net, the net power, is shown going out of our black box system operating in a cycle. That's how we can tell it's a power cycle, also known as a heat engine in thermodynamics talk. Over here, similar, looks similar. Oh, no, it's different. Here, the power is going in. Oh, and I didn't say much about the heat transfer over on the power cycle. So let's look at the heat transfer for the refrigerator, air conditioner, or heat pump sketch. Our heat flow is going from the low temperature reservoir TL up into the cycle, and then we're rejecting heat or we're moving heat up to a high temperature reservoir. Look at those arrows. Compare it to the arrows over here. Look, this is a heat engine. We're transforming high temperature heat transfer into the system, into some net power. But the second law says we must reject at least some heat to a lower temperature reservoir. Okay, that's the basic idea. If it's Greek to you, turn this video off and go watch Carnot Cycle 101. Okay, so you think, well, I'm working through this class. The class is a pain. Gosh, why do I need to? I'm assigned to take this class. I've just got to get through it. At least I want to demonstrate to you what's in it for me. What's in it for you? I had those same questions. What's in this material for me? I'd like to illustrate something like that for you. And so Carnot cycle analysis gives you a powerful tool for quantifying the best possible performance of a proposed great idea. Okay, so here's a refresher course in the material. Okay, we've got a power cycle, also known as a heat engine. Okay, how would we describe the thermal efficiency of a power plant or power cycle? It's the energy sought over the energy that costs. I've had some great conversations with students on what does this sought and cost mean? What does that mean? You have to imagine that you own a power plant. If you own the power plant, what you're seeking to do, your objective is to sell electric power to consumers to make money, to generate revenue, to keep yourself in a job, and to keep those people that work for you in a job. That's the energy sought. Okay. And what does it cost you if you own a power plant? What does it cost you other than salaries and maintaining equipment? What's a big cost? What's a big cost of running a power plant? Well, it's buying the fuel. It costs you money to buy the fuel. It doesn't even matter what that fuel is, what that heat source is. You've got to buy it. You've got to purchase it. Energy that's sought is Q dot H. And so that's how we come up with this formula that you may be blindly using. I hope you now understand what's behind W dot net over QH. Q dot H is the measure of thermal efficiency of a power plant. And then in class, we said, now we're going to apply the first law of thermodynamics for a cycle to change W dot net into Q dot H minus Q dot L. In other words, this heat flow minus this heat flow must exactly equal this net power rate of producing work, kilowatts. Okay. And then later in class, we talked about the Carnot cycle, which is the best internally and externally reversible cycle. It's the best you can possibly do and satisfy the second law of thermodynamics. It says the Carnot thermal efficiency, in other words, the maximum thermal efficiency is, you can derive this, TH minus TL over TH. It's expressed in terms of these temperatures of the reservoirs. And remember, these temperatures must be an absolute temperature. But wow, now you've got something that's actionable, something you can study and quantify as long as you have a value for TH and a value for TL. And in the real world, we have those. We can estimate those. A refrigeration cycle. Now remember, refrigeration cycle is also the same as an air conditioning cycle. These are the same basic pieces of equipment. We describe the measure of performance for a refrigerator or air conditioner, beta refrigerator, as energy sought over the energy that costs. Now you've got to use your common sense. What are we seeking to do for a refrigerator or an air conditioner? We're interested in keeping you cool. Here's you. Here's a picture of you in a lower temperature. You're trying to stay cool at TL. Okay. That's energy sought, okay? Energy that costs. Well, we have to plug our air conditioner or refrigerator into the wall to utilize electric power going into this black box. And then we're going to reject an amount of heat to a higher temperature area, to the surroundings that are warmer than what you're trying to be. Okay, energy sought over the energy that costs. Beta is Q dot L sought over W dot net costs. Then we apply the first law for W dot net. It's Q dot H minus Q dot L. And then we see a similarity you can derive in class. The coefficient of performance for a Carnot cycle, that reversible cycle, is simply TL divided by TH minus TL, and look at the similarity. So it's not a matter of looking at formulas on a formula sheet. Look how similar. You should be able to remember this relationship, I hope, okay? We're going to get to some example problems on this, but finally, we're going to cover a heat pump. What's a heat pump? Well, let's look at this. It's the same sketch, except the stick figure is moved. You have moved up to a higher temperature. And so a heat pump, the objective of a heat pump is to transfer heat into a room where you're sitting or standing. That's the higher temperature compared to the cold outside, TL. Okay. And what does the heat pump do? Well, we have to purchase electric power from the wall, from the grid, from that power plant manager. And so we're going to run our system operating in a cycle, and we're going to transfer heat from the low temperature outside surroundings up into the room. It's really kind of cool. Okay. And so we do the same derivation. Energy sought over the energy that cost. This is gamma for a heat pump, Greek letter gamma. Energy sought, Q dot H. We look at the sketch, trying to keep you warm, Q dot H. That's what we're seeking to do. Divided by energy that costs us. For this example, it's W dot net. It's the power we have to buy. We apply the first law. Look at the repetition we've got going here. Q dot H divided by Q dot H minus Q dot L. You can derive for a Carnot cycle the maximum possible thermal coefficient of performance. And look, I've got a little typo here. This is gamma of the heat pump Carnot. This should be gamma of a heat pump maximum. Copy and paste error equals TH divided by TH minus TL, and look at the similarity. So it's my hope that you've got these things in your head without going to a formula sheet, because you're going to be able to use these to great advantage when you're a practicing engineer. Okay, so just to summarize, and we're going to get to the examples. If the measure of performance, whether it's Greek letter eta, whether it's beta, coefficient of performance, or gamma, coefficient of performance for a heat pump, if that measure of performance exactly equals the Carnot measure of performance, then the cycle is possible and reversible. It's the best you can do. If the measure of performance of a cycle is less than the Carnot measure of performance, then the cycle is possible and irreversible. And this is the area that we observe most real-world cycles. They're obviously possible because they work, and they're irreversible. And then finally, someone's brought a good idea to the table, and we analyze that great idea. If the measure of performance of a proposed cycle is greater than the Carnot measure of performance, then that proposed cycle is impossible. And you as an engineer can explain that to the person bringing the great idea to the table. Very powerful for you as a practicing engineer. Okay. And so I'm going to have to move my Zoom. So you have the ability to evaluate great ideas that come to the table. And here's a little sketch of you. You may be working on a team, an engineering team, a design team, a good idea team on where can we either make more money or save energy. Very common. So these great ideas might be yours, or they might be somebody else's. And your job can be to check these good ideas. Are they possible or are they impossible? Or how much can I do? How much benefit could I get from this good idea? So here's great idea number one. I have had so many of these great ideas myself, and other engineers have brought these great ideas to me as a supervisor. Great idea number one, generate electric power from a waste heat source at your workplace. And so here's this is an example. Engineer says, I have identified a source of waste heat, look at that, in our manufacturing process at a constant temperature of 400 degrees F. So I'm sure perhaps this exhaust gas is coming out of the stack at 400 degrees F, and it's currently unused. It's just going to the atmosphere, heating up the atmosphere. I've estimated that the waste heat amount is available from this exhaust stream at a rate of 100 kilowatts. I've estimated that. How much electric power could I possibly produce from this waste stream when rejecting heat from my little power plant to the surroundings at 75 degrees F? So in other words, the surroundings are at 75. How would we quantify that? I'm going to suggest you can do that right now today. Here's how we do this. Okay. You're going to say, the best I could do, the best power plant I could get would be a Carnot cycle. That would be the best I could possibly do. I know that I'm not going to be able to buy a Carnot cycle off the shelf, but there are many power plants that I can buy off the shelf. Start with a sketch. We've got 100 kilowatts of heat transfer coming from a high temperature heat source at 860 degrees R. You see how I changed 400 degrees F to degrees R, added 460. Okay. Also, I'm rejecting heat at 535 R. So I've got absolute temperature. Here's my sketch. Okay. Next step is to remember thermal efficiency for a power plant, for a Carnot cycle power plant, is TH minus TL over TH, plug and chug. Okay. So the maximum possible thermal efficiency is 37.8%. I've got 100 kilowatts of Q dot H. So let's see. I apply the definition of thermal efficiency to solve for W dot net and get 37.8 kilowatts. And so the answer for this commonly asked question is, you can get, if I could buy a little power plant, I can transform 100 kilowatts of heat transfer rate into 37.8 kilowatts of net power. That would be the most I could do. I would predict I'll get less. And I'd do some more engineering to quantify that. But at least you've got an upper bound of how much maximum power you could produce from this waste heat stream. I got to tell you, I got so much mileage out of this skill that I got from, in my case, first quarter thermodynamics. Great idea number 2. Generate electric power from a geothermal heat source. I'm going to bet that every one of you watching this has heard of geothermal heat sources. It's an untapped or little tapped source of heat from the earth. And it doesn't cost much, right? It's basically free. Here's the idea. This is a picture of Yellowstone National Park, these very hot water ponds in Yellowstone. I've identified a source of geothermal energy available at a constant temperature of 200 degrees F. So throughout the year, this pool of hot water is sitting there nearly boiling. It's at 200 degrees F. I've estimated that the rate of available heat transfer from this pond is 250 kilowatts. I've done some engineering analysis. I've been through heat transfer. I've estimated 250 kilowatts of heat transfer rate is available. How much electric power could I possibly produce from this heat source when rejecting heat from my power plant to the surroundings at 70 degrees F? I can quantify this. Let's see how this compares to example number 1. Okay, we're going to go through the same idea. Let's see, sketch is the same. I've transformed my temperatures into absolute temperature. In this case, I've got 660 R, that's 200 degrees F, and 530 R, see, okay, that's 70 degrees F. And I've done some analysis, and I've got Q dot H is 250 kilowatts. Plug and chug, I've got the mathematics. TH minus TL over TH is the Carnot thermal efficiency. The maximum possible thermal efficiency for this good idea is 19.7%. It's the best I could do. But I'm going to run the numbers and report that if I've got 250 kilowatts available, I can transform that rate of heat transfer, Q dot H, into 49 kilowatts of electric power. W dot net. Cool. And look at the dollar cost of the energy is very low. The dollar cost of the energy, extraordinarily low. Good idea. Now, you say, man, that gives me some ideas. When I go out and get a job, I want to, if you download the static slides, and I think I'll be providing a link so you can download the static slides, you can go right to a government agency, the U.S. Energy Information Administration, and you can learn a lot more about geothermal energy at this link. Okay, next, we're going to use sort of almost like the flip of geothermal energy. Great idea number 3 is to supercharge your heat pump at home, using the earth as a heat reservoir. We're seeing this being done more and more and more as the cost of energy goes up and up and up. The cost of electric energy goes up and up and up. Here's the situation. Now here's a little background. I'm quoting a scientist, and you can click on this link. It says, the temperature of the earth down 20 or 30 feet, you got to dig a little bit, is relatively constant year round, somewhere between 50 and 60. So if you can get a backhoe and dig 20 or 30 feet down, the temperature of those surroundings of the earth is going to be between 50 and 60. That's amazing. All right, so here's the great idea. So a heat pump is commonly used system operating in a cycle for residential and commercial indoor heating. That's our heating source in the winter, is an electric heat pump. The traditional heat pump condenser component uses the outdoor surroundings as its low temperature heat reservoir. So we've got our condenser out there, and it's out there in the cold, right outside, right behind me here. Now, what we want to do is we want to plot the Carnot cycle heat pump coefficient of performance for outdoor temperatures ranging from -5 degrees F, that would be the dead of winter, up to 60 degrees F, that would be the spring, okay, and a constant indoor temperature of 68, and compare that to if we could bury our condenser, if we could transfer heat from the outside instead of at -5 at, let's say, 58 degrees F, a constant year-round temperature of 58 degrees F. We're going to do that and compare the coefficient of performance for our heat pump for those situations. Okay, so let's start with a sketch for our analysis. Here is our real-world sketch. Here's me inside at 68 degrees F, okay, inside, okay. Here's the heat pump operating in a cycle. We're buying electric power. We're transferring heat from the outside. And in the dead of winter, our outside is -5 degrees F. In the spring, when we don't really need much heat, it's 60 degrees F. So this is my sketch for the real world. Okay. Here's a proposed project. Here's me again. Okay. System operating a cycle, but this time we're going to bury I should have said evaporator, but just excuse me for that. We're going to bury the evaporator section of the heat pump down at a constant temperature of 58 degrees F, 20 feet below the surface. Okay, so it would be the evaporator section. So just excuse me for that mistake. Here's option 2. Good idea. We're going to refresh our memory on how do we quantify the coefficient of performance beta for a heat pump. And then for the Carnot cycle, the best you can do is going to be TH divided by TH minus TL. As long as we work in absolute temperatures, TH divided by TH minus TL. Let's do the math. And here's the math. Okay. So for our good idea, the coefficient of performance for a Carnot cycle heat pump is 52.8. That's amazing. What does that mean? Energy sought over the energy that costs. It says that we're getting about 53 times more kilowatts into the house compared to the kilowatts of electric power we're purchasing to run that heat pump. That is amazing. Now, unfortunately, we can't buy a Carnot cycle heat pump. We can't buy that off the market. It doesn't exist. All right. But this is going to give us an idea of the best we could possibly do and compare to what we have in the real world. So if we had a Carnot heat pump on the ground and we're calculating that exact same coefficient of performance for a bunch of different outside temperatures. So an outside temperature of -5. So in the dead of winter, even a Carnot heat pump would be operating at a coefficient of performance below 10. Below 10. Okay. Wow. Okay. And then you observe that the Carnot coefficient of performance gets better and better and better as our low temperature, as it warms up outside. And this is the same behavior that we observe in the real world. So this gives us a way to compare, a way to study a great idea. And so this, based on the economics, this could be a great idea, depending, especially if you are in an area that gets very, very cold. Okay, so potentially a great idea. So look at that comparison. Okay, and this is making my point. So look at this comparison of coefficients of performance to this geothermal heat pump where we have buried the evaporator section down in the ground for a constant temperature of 58 degrees F, okay, compared to when it's really cold outside. And then the only time that this is not a good idea is when the outside temperature is 60 degrees F. But you don't really need much heating anyway, right? So you're losing ground with this, but you don't really need, you need very little heat for this situation. So this is potentially a wonderful idea to exploit geothermal heat sources. Okay, and again, you can learn more at GeoExchange to learn more about how real world, this is a schematic of a real world heat pump situation that's absorbing heat in the evaporator section from deep ground energy. A great idea. Same idea. And you can also go to the EPA.gov to learn more about geothermal heating and cooling technologies. Great ideas. All right. Here's the last great idea. And this one I'm looking ahead in your career a few years. Another great idea for electric power generation from a waste heat source. Going to be similar to idea number one, but I've changed the situation. And I want you to imagine that you are an engineering supervisor. In other words, you have worked as a practicing engineer for a few years, and you've been promoted to a supervisory position where there are a handful of engineers reporting to you. And one of your sharp engineers has come to you with this great idea. So I'm going to read this great idea that a sharp engineer that reports to you would come to you with. Okay, engineer says, I've identified a waste heat source in our plant where a heat at a rate of 10 megawatts is available. Waste heat at a rate of 10 megawatts is available at 400 degrees C. 400 degrees C, that's really hot. Okay. I've designed a power plant system whereby we can produce electric power and reject the leftover heat to the surroundings at 23 degrees C. Okay, so that's the deal. And the engineer's done some further analysis, said, I have determined that with my proposed power plant, I will produce 7 megawatts of net electric power to pay for the needed power plant components. So the engineer's sharp and understands you got to pay. We don't just get power plants for free. We have to pay for them, okay? And then finally, the engineer says, when can I get this capital money to begin my great project, to put myself on the map? I'm ready for the money. I'm ready to run this project. So as a supervisor, what questions do you ask your engineer before you start scrambling around to find the money to give to your engineer? When can I get capital money to begin the project? Wow. Eager engineer. Here's things that think about what would you ask if you're the boss? What would you ask that engineer? Okay, so here's a summary. Waste heat available 10 megawatts, Q dot H, 400 degrees C is TH. We propose, he or she proposes to make 7 megawatts of net electric power and reject leftover heat. So the engineer is recognizing, I can't convert all of this heat transfer into power. Got it. Sharp. Okay. I'm going to reject that. What kind of things would you ask? Well, let's see. Here's what comes to my mind. Well, you've stated enough in your proposal to determine the thermal efficiency of the power plant. It's going to be 7/10, 70%. Okay. Did you compare this to the thermal efficiency of a Carnot cycle? Great question. Good first question to ask. In other words, with the data that you have, did you calculate Carnot thermal efficiency and compare that to 70%? And is your proposed plant possible or is it impossible? Next question. Well, how much will the whole project cost? I do see that you have done some cost estimates, but I'd like to see a cost summary of the work you've done. So a good supervisor has got to see at least a summary presentation of the cost estimate of the capital, because the next logical question that the supervisor must ask, because that supervisor has got other supervisors, like maybe the owner of the plant or the supervisor, the manager of the plant, what is the return on investment for your proposed project? In other words, what income stream will we have compared to the capital cost? Engineering economy. What is the return on the investment for your proposed project? And look, if your engineer knocks your socks off and answers all these questions, you, as the supervisor and the engineer, are going to race to your manager or the owner of the plant and say, we've got a great idea, or this engineer has got a great idea. Appreciate that person bringing it to me, and let's see if we can move ahead with that great idea. So what's your great idea? I'm going to bet that now that you've been through thermodynamics class and you're getting more skill in energy transformation from heat to power, heat to work, I'll bet you've got some great ideas. So this is sort of an open-ended question. What's your great idea? I do want to suggest that your great idea could be a game changer. It could be big. It could be big for your career, or it could be big in general, in terms of benefiting lots and lots of people. So the sky's the limit. I want to encourage you to explore and quantify your great idea. So it's up to you to communicate your great idea to those you work with, understand the fundamental limits, power of the Carnot cycle, and then go for it. And so look, the rest of this is up to your imagination, your determination, and your drive to do your best and to make things better. So I suggest you go for it. And that covers it. I hope I've given you some ideas on how to quantify. What's the value of this class you're taking? I would suggest that it's really got a good value to you as you are preparing to be a practicing engineer. So hope to see you again on another one of these videos.